We live in a world of three dimensions: length, width, and height. These dimensions define our physical world, but there's another dimension we often overlook: time. Time, as Einstein revealed, is not a constant tick-tock, but a dimension interwoven with space itself. This four-dimensional fabric of spacetime is the true stage on which the cosmic play unfolds. Imagine a flat sheet, that's your familiar three-dimensional world. Now picture that sheet bending and curving. That curvature represents the influence of gravity, a force that warps both space and time. Just as a ball rolls downhill, objects in spacetime follow the curves created by gravity. But here's where things get really interesting. Our motion through spacetime isn't constant. We speed up, slow down, and change direction. And these changes in motion actually affect our experience of both space and time. Buckle up, because we're about to explore the mind-bending consequences of this four-dimensional reality. Let's picture a racing car zooming along a track. From our stationary viewpoint, we see the car moving across a fixed distance in a certain amount of time. But imagine you could ride along with that car, matching its speed. What would you experience? As you approach the speed of light, something incredible happens. Time itself begins to slow down relative to someone standing still. This isn't just a theory, it's been experimentally verified countless times. The faster you move, the slower time flows for you relative to someone at rest. This phenomenon, known as time dilation, is one of the most profound consequences of Einstein's theory of special relativity. It tells us that time is not absolute but is relative to the observer's motion. Now let's consider another mind-bending effect of high-speed travel length contraction. Imagine a long pole traveling at near light speed. What would happen to its length? From our perspective, as the pole moves faster and faster, it would appear to shrink in the direction of motion. This isn't an optical illusion. The pole's length is actually contracting in the direction it's traveling. This occurs because the front and back of the pole occupy different points in time from the perspective of a stationary observer. The faster the pole moves, the greater the difference in time between its front and back, and the shorter it appears to us. In everyday life, we take for granted that now is a universal concept, but in the realm of four-dimensional spacetime, now is relative. Just as our perception of space changes depending on our motion, so too does our perception of time. Imagine two events happening simultaneously in different locations. From our perspective, they occur at the same time. However, for an observer moving at a different speed or in a different direction, these events might not be simultaneous at all. This relativity of simultaneity has profound implications. It means that there is no single universal now that everyone agrees on. What we perceive as the present moment is just a tiny slice of a much larger, four-dimensional reality. Our understanding of four-dimensional spacetime is still unfolding, but one thing is clear: the universe is a far stranger and more wondrous place than we ever imagined. Through continued exploration and experimentation, we inch closer to unraveling the secrets of this mind-bending cosmic tapestry.